Am I audible? Can anyone confirm?
Yes, sir, you are audible.
Okay, so now we can start the lecture. Before that, let me check whether the recording is on or not. Yeah, recording is on. So, good afternoon, everyone. Today is the week fourth of the tutorial session in the Deep Learning IIT Ropar course. So, today we'll discuss some of the important questions or the questions which can build the concept from the week four lectures as you have already studied. Yeah, that is uploaded on NPTEL portal. So we'll start with the basic questions based on the learning rate. And it is very good if you guys answer the question in the chat box as well. And if you have any doubt, then you can ask in chat. So the first question is, which of the following statements is true about the learning rate alpha in the gradient descent? So alpha is our learning rate and it's asking which statement is true among all these four given statements. So the first statement is if alpha is very small, gradient descent will be fast to converge. If alpha is too large, gradient descent will overshoot. But as we have studied in the lecture series, that if our means learning rate, if alpha is like, we'll change the pen color. What happen if alpha is small? The gradient descent will be very slow to converge. Okay, like it will take lots of time and it will slowly converge. Okay, and when alpha is large, then at the point of optimization, like where we can get the minimum loss, there it can overshoot, and the gradient descent will overshoot if the alpha is large. Okay, so if when alpha is large, it can overshoot where the at the optimization point. So which option is correct? As you can see here, the option B, that if alpha is very small, gradient descent can be slow to converge. Yeah, this is the first part is correct. Second, if alpha is too large, gradient descent will overshoot. Okay, where the loss is minimum. Let's suppose this is our curve. If our learning rate is too high, let's suppose we are here. So we can, this is our minimum point. So we can go up to this position if our alpha is very high. So it can overshoot. So option B is correct. You can reply your answer in the chat box also. I will be opening that and we'll read the chat, your chat means in chat box also. If you have any doubt, then you can ask in this first question. So some of the concepts you can see based on the learning rate. First of all, the learning rate is a hyperparameter. What is hyperparameter? Like hyperparameter are those parameters which control the other parameters. Like it is the supreme level parameters. Like it does not depends on W or B. It is independent of those normal parameters, and it can control the other parameters like W, weights or bias, and the other parameters as well. So learning rate is a hyperparameter. The first thing about this, it is used to control the rate at which an algorithm updates the parameter estimates. Okay, and it is used to scale the magnitude of parameter updates during gradient descent. So depending on the learning rate, like how frequently our parameter will be updated, that depends. Okay, and learning rate is a scalar, a value that tells the machine how fast or how slow to arrive at some conclusion. Second, effect of small and large learning rates, as we have seen in the first question as well. Like if the learning rate is too small, learning will take long time to converge. Okay, it will slowly converge to the optimization point. On the other hand, if the learning rate is too large, Like if learning rate we takes very large, then at the point of optimization, it will overshoot, and we have to take again the U-turn to come back to the optimization point. So it may miss to converge. So these are the properties of learning rate. Third, in gradient descent, like what is gradient descent? In machine learning, gradient descent is optimization algorithm which is used to learn the model parameters through back propagation. This algorithm works in iteration to find the local minimum of a cost function. Like why do we learn the parameters W or B, whatever? So that our cost function, that is a loss function, that should be minimum. Okay, error should be minimum. So any doubt in the first question? Like many students joined now. So this is our first question. So this is just a simple question. Like which of the following statement is true about the learning rate uh, alpha in the gradient descent? The answer is if alpha is very small, like if learning rate is small, it will slowly converge. And if alpha is large, what will happen? Gradient descent will overshoot. So option B is correct. If you have any doubt, you can ask in the chat box. Now coming to the next question, that is based on the contour map. Uh, First we will see the contour map and then we will solve this question. This is our contour map. Okay. So now this is our this is a 2D contour map, and we have to guess the 3D surface. So this is already well described in the lecture, but for this question I will also explain little bit. Like here you can see uh, this point is somewhere at this point in the 3D surface. So what happens when there is a large distance between the contour map, like between the surfaces? Like here you can see there is a large difference between the next surface, like next boundary. So what happen? Then our slope is very flat. Okay. So a large distance between the contour indicates the gentle slope along the surface. Okay. So here how our slope will be, like it is starting from here. So this slope is very gentle. You can see the slope is very gentle, like almost flat. So it is moving up to this point. Now again, now you can see the next boundary on this contour map is very nearby. So when there is a small distance between the contour, indicates a steep slope along that direction. Okay. So now the slope will be very steeper. Okay. Any doubt in this? Uh, and again, it will be like very steeper. So here this will very, it will go little inside. And after that, what happened? Like when we move towards this end, again, like there is a large distance between the contours. So what will happen? In this case, again, our slope will be little flat. So it will convert like this. So this is the 3D surface derived from this 2D contour map. So anyone is having any doubt in this? Just remember two important points. The first one, a small distance between the contours indicate a steep slope. That means a very high value of slope along that direction. Okay, like in this area, there will be a steeper slope. Okay, and a large distance between the contour indicates a gentle slope or the flat surface in the 3D surface visualization, as you can see. So like here you can see there is a large distance. So in large distance, slope will be very gentle. Here slope will be steep. So this is the error surface as shown in the 3D view. Any doubt in this question, you can ask in the chat box. I have not seen any doubt. Okay. So now moving to the question 2, as we have seen the concept. Which of the following is true with movements in the contours map? The first statement is given smaller gradient for gentle slope. Second option is smaller gradient for a steep slope. Third is large gradient for gentle slope and larger gradient for a steep slope. So which options are correct? Can you answer in the chat box? Like you can see here, when the first option is small gradient for gentle slope. Like when the slope is gentle, like in this area, I will take some other colored pen. Hmm. So in this area, you can see slope is very gentle. So at this area, the gradient will be very small. Okay. Because there is very less change. And in this area, that is a valley area, in this area, gradient will be high. Okay. For a steep slope. For a steep slope, gradient will be high. As we have already discussed this. So which option is correct? Like statement 1 is correct and statement 4 is correct. So option A is correct. Any doubt in this question? You can ask. And this video is also recorded. Like if some of you are not able to understand now because you have not seen the week 4 lecture, then you can watch on YouTube channel. That is also shared on the NPTEL portal. So this video will be recorded and uploaded on YouTube as well. But from this tutorial session also you can understand the basics which was taught in the week 4. Then it will be easy for you to study the week 4 lecture. Now coming to the next question, this is pick out the number of steps in one epoch for mini batch gradient descent algorithm. First of all, we will see how to determine the number of steps. Yeah, Vasanti P replied N by B, option C. Yeah, that is the correct option. So we will see how to determine the number of updates, that is also known as number of steps. Like one epoch is like I means passing through the entire data. Like whatever the values are given in the data, we are just scanning through the entire data. That is known as one epoch. Okay, and one step is the uh, like update in the parameters. Like after scanning, if we update the parameters, that is known as one step. Okay, this is the updating of parameter. N is equal to number of data points, and here B is the mini batch size. So for our algorithms, like that is normal gradient descent, that is vanilla gradient descent, how many times it updates in one epoch? It just update only once. After scanning through all the data points, it updates the parameter only once. So here for vanilla gradient descent, number of like updates, or that is the steps in one epoch, that is one. For stochastic gradient descent, how many times? It will update n times. Okay, for each points. Like for each points in the data, it will just update the parameters one by one. So that will update n times in the stochastic gradient descent. Now, if we take a batch size of B in the batch gradient descent, that is also known as mini batch gradient descent. So in that case, it will update n by B times. Okay. So in coming to the question now, pick out the number of steps in one epoch for mini batch gradient descent algorithm. So the option C is correct, that is n by B. Okay. One is for vanilla gradient descent and n is for stochastic gradient descent. Okay. So now we will move on to the question number 4. So any doubt in this question number 3? One is for vanilla gradient descent, n is for stochastic gradient descent, and n by B is for the mini batch gradient descent. These many times the parameters will get updated. Okay, in one epoch. Okay, nice. So now we'll move on to the next question. That is our question number 4. Sorry for this mistake. The heading of this is gradient descent only, because we are discussing question based on gradient descent. The last slide was correct. So coming to the question number 4, the update rule for momentum based gradient descent is given by update t, gamma update t minus 1, like it is looking at the previous observations also multiplied with eta into gradient. So which of the following is true for the given rule? So before solving this question, we'll see some of the concept part. Like in momentum based gradient descent, how we update the parameters, we just consider the previous observations also, and accordingly wt plus 1 is equal to wt minus update at the time instant t. So what is update t? That is equal to wt minus, okay, so this will be our wt plus 1. In this, it just take the previous observations also, and accordingly it just update the uh, w value, okay, in this momentum based gradient descent. And after that, there is a one problem in this, if this is our curve and this is the minimum value of the loss function, this is loss curve, so this is like optimum value here. So let's suppose we are here in this curve. So in the next step, it will again go up to here, and then again it will come back. Okay. So it will just oscillate a lot at the point of optimization. So this is the demerit in the momentum based gradient descent. Now what happened in Nesterov accelerated gradient descent? It's take consideration of look ahead. Like the next step is this. This is momentum based gradient descent. So it will oscillate here. The oscillation will be very high here. Now coming to the next, that is nag. In this is our loss curve, and this is our point of optimization. So what happened? Now we have taken the W look ahead. That depends on the previous value of W at the previous time stamp t minus update at the previous time stamp. That is update at t minus 1. Okay. So now we have calculated the W look ahead, and accordingly we'll update the parameters. Now wt plus 1, that is equal to wt minus update of t. Now update of t, here you can see there is one value, that is gradient of w look ahead. So we are taking the gradient of look ahead. So let's suppose we are at this position now. Like in the next step, we are moving here. So this is our look ahead position. Okay. At this place, this is our w look ahead. So now we know that we have to, like we have already seen that we have reached the like here we have crossed the optimum point. So we have to take the U-turn. So now we will take the gradient of W look ahead, and we know that we have to come back. So we will not take this much higher step here. So here the WT plus 1, this update is taking consideration of W look ahead. So it will not take this much higher jump. It will take somewhere about this position. Okay. Because we already know our next position, that is W look ahead, using the momentum, using the previous, like the data based on the previous timestamps. So now it will come here. So here the oscillation is very small as compared to this momentum based gradient descent. So here oscillation is very high. In this, oscillation is very small. Okay. There will be some oscillation here also, but it will be a small oscillation. So this is the advantage in the NAG. So now coming to the question, that is the update rule for momentum based gradient descent is given by this equation. Which of the following is the uh, true for the given rule? The first option, history is never taken into account. This is wrong. As you can see, this update t minus 1, this depends on the history, like depends on the past observations. Okay. So option A is wrong. Now option B, that is always take a step only based on current gradient. This is also wrong because it takes consideration of the previous gradient also. As you can see, wt plus 1, that is equal to wt minus, here update t is there. So this takes the gradient of wt. Okay, that is the based on the previous observations. So option B is also wrong. Coming to the option C, takes a larger step as only history is taken into account. Option D, take a larger step as in addition to the current step, history is also considered. Okay, so it takes a larger step as we have already discussed in the curve in addition to the current step. Okay, and history is also considered. So option D is the correct option. Okay, so how many of you answered the option D? Yeah, you have answered correctly. So the option D is correct. Any doubt in this question? You can see the equation for these. If you have any doubt, then you can ask. Else we will move on to the next question. Okay, so we'll move on to the next question. So now we have already discussed the advantage of Nesterov accelerated gradient descent and also discussed how it works. So the next question is, which of the following is the advantage of NAG? Okay, that is Nesterov accelerated gradient descent. So there are four options. It will be very easy question. So just answer. Option D. Okay, let's see. Always escapes minimum value. Like it cannot escape minimum value as we have seen in this curve. It will also oscillate, but it will oscillate very in a smaller amount. Okay, slower than the momentum based gradient descent. No chance of escaping minimum value. That is also wrong. And the fourth option, that is smaller oscillation. The option D is correct. Okay, so right answer. Yes, Navendu and Vasanti. Okay, option D is correct. So any doubt in this question? So now we will move on to our question number 6. So if you have doubt up to the previous fifth question, you can ask in the chat box. No, then we can move ahead. So okay. Now the question 6 is, what are the reasons for taking a running average of the gradients at MT? Okay. So why we take running average? Because we don't want to rely too much on the current gradient and instead rely on the overall behavior. Like that is average of the previous like overall behavior of the algorithm. Okay, so what we do, we take the running average here. So which option is correct? This is very simple question. We just want to consider the overall behavior of the gradients over the different time stamps. We don't want to rely only on the current time stamp t. Okay, so the option A is to rely on the current gradient. That is wrong because we considered at time t minus 1 also. like we do, this is the formula. Mt is equal to b1 mt minus 1 plus gradient of w. So here you can see mt depends on mt minus 1. So option A is wrong. Option B, to rely on the behavior of gradients at particular time step t. This is also wrong. Option C, to rely on the overall behavior of gradients over many time steps. So this is the correct option. That is also given in the reason here. The reason we are doing this is that we don't want to rely too much on the current gradient and instead rely on the overall behavior of the gradients over many time steps. So option C is correct. Let's see any of you have answered or not. Okay. So actually this is the part of the update rules for Adam. So I guess most of you have studied this in the week 4 lecture. Now coming to the question number 7. What is the number of updates for the vanilla gradient descent algorithm after going over the entire set of 1 million data point thrice? So here in this question, this is based on the previous question what we have done here. This question number 3. So, uh, in this question, we are going through the entire set of 1 million data point thrice. So this means number of epochs is equal to, what will be the number of epochs here? 3. Okay. So now in one epoch, in vanilla gradient descents, how many times it updates? 1. So in 3 epochs, how many times it will update? 3. Okay, option A is correct. Any doubt in this? Because we know in vanilla gradient descent, the parameters are updated once if number of epoch is equal to 1. So here we are going scanning the entire data set thrice. So number of epochs is 3 here. So very simple question. Option A is correct. Okay. So now coming to the question number 8, that is, consider a stochastic gradient descent algorithm run over a million data points. We observe that there is an oscillation. In order to reduce this oscillation, we try to implement mini batch gradient descent. Comment on the accuracy of the estimates. Okay. So which option is correct here? So here this is the concept of mini batch gradient descent. Option B, yeah, right. Option B is correct. So in this question it says that consider a stochastic gradient descent algorithm that is run over a million data points, data sets having a million data points. We observe that there is a oscillation. In order to reduce the oscillation, we try to implement mini batch gradient descent. So what happens in mini batch gradient descents? Let's suppose our batch size is k. So the next update that will take place depending on looking at the k points. Okay. Next update takes place depending on looking at k points. In a stochastic gradient descent, it just look at one point and update, but that is not comfortable for the nearby other points. Let's suppose this is our, again we'll take the same curve because this is very simple. This is our optimization point. So if here we look at the one point, and that suggests us to go. This example is not suiting here, so we can ignore. But just you think like if we just take a one point in consideration in the neighborhood, and then that tell us to like take some updates, that will be not much reliable when we are taking updates based on the taking k points, looking at the k points and taking the updates. Okay, so the option B is correct. The accuracy will be increased when we take the batch size of k and takes the update accordingly. So now the next is based on the line search. We have one question. Which of the following is a drawback of line search technique? Just answer this question. Yeah, more computation is required. Like in practice, why we do line search? To find a relatively better value of learning rate, and it updates the learning rate. It is like looking at at each steps. It is updating the learning rate, and this updated learning rates depending on the each steps. So like at each step that will be the optimized learning rate at that point, and also the loss will be optimized. That will be the minimum loss for that learning rate. So here we can see these are the four options. So like this simple question, it takes more computation because it update at each step. So it will obviously take more computational time, because if you update at each step, then it will take more time and even the more computation. So option B is correct. Now moving to the question number 10th. Yeah, Vasanti, option B, that is correct, right? So like the for the toy example discussed for ADA grade in the class, it happened that it got stuck before it could reach convergence. Like our parameter got stuck before reaching the convergence. This was because of the decayed learning rate. How does RMS prop overcome this? So what will be the answer? The option is higher learning rate, different values for learning rate. It is less aggressive when decaying the learning rate, and it is more aggressive when decaying the learning rate. So like ATA grade is more aggressive when decaying the learning rate. So what does RMS prop do? It will just uh, become the less aggressive when decaying the learning rate. So as we know, in ATA grade, we can write it as this is the equation, and here Vt is equal to Vt minus 1 plus delta Wt square. So gradient of Wt square. So here you can see this Vt that is in the denominator, and what it will do, it will like if it is lesser value, then like the learning rate value will increase. So it is just become the it is like reducing the learning rate to decay faster. So the option C is the correct option. It is less aggressive when decaying the learning rate. Sorry, this is for this ADA grade, and we use one more parameters in this RMS prop, that is based on the, like we take some constant beta and multiply in the denominator as mentioned in the class. Like I can show you the slides. So see here, this is for Adam. This is for ADA grade. Here it depends on VT, that is the square root. Now we'll see for RMS prop. Here you can see in RMS prop this beta is taken. Okay. So now the VT value will decrease here. Uh, like this denominator will decrease here. So what happens as a result? ADA grades decays the learning rate very aggressively as the denominator grows. But here beta is like less than 1. So, so what happened? Our denominator is, to avoid this, why not decay the denominator? Like our denominator is decayed and prevent its rapid growth. Okay. So this is in the update rule for RMS prop. So this, in this learning rate are like decayed little. Uh, like in the ADA grade, the learning rate is like very aggressively decaying. So just to controlling it, we are using this term, this parameter beta and 1 minus beta, so that it should not decay that much. Okay. Like when our denominator is uh, like less, then this whole term will be little more. Like if denominator is controlled and decrease, then the overall this term will be increasing. This term will increase. This means this is preventing it from the rapid growth. Okay, like it preventing it from the rapid decaying of the learning rate. That is done. Like that is a problem in the ADA group. Okay, so in this, it is less aggressive when decaying the learning rate. This is the advantage of RMS probe over this ADA group. So now we'll move on to the next question. This is also depending on the number of updates. Like you have to see all the lectures in the week 4, then you will understand all these questions here. Let's suppose we have 50,000 data points and mini batch size being 5,000. Like here, our n is 50,000 and the batch size in the mini batch size is 5,000. So this means k is 5,000 here. One epoch implies one pass over the data that we have already discussed. What is one epoch? And one step means one updates of the parameters. Okay. Like if you take one steps means we are updating the parameters once. So what is the number of steps in one epoch for all these algorithms? So like it is asking how many times our parameters will get updated. So the first is mini batch gradient descent. In mini batch gradient descents, we know that the number of steps, that is like number of times the parameter will get updated, that is equal to how much? N by k. So here it will be 50,000 by 5,000. So it will be equal to 10. Okay. Now in stochastic gradient descent, how much it will be? It will be N. Okay. That will be equal to 50,000. In vanilla gradient descent, it will update the parameter once after going through all the data points. So that will be equal to 1. As we have already discussed this here, like here you can see the formula. 1 is for vanilla gradient descent and N is for stochastic gradient descent, and for mini batch gradient descent it is N by B. Okay. So the answer is, for the first part 10, for the second part that is N, and for the third part that is 1. So any doubt in this? So like till now, if you have any doubt in any of this question, then you can ask. If no doubt, then I can take some of the concepts. Okay, so no doubt. So we'll move on to the next question. That is like how to, not a question, just I will just I would like to just explain this concept. How to choose the appropriate learning rate. So how it can be done? Like there are so many values, but how we can take the learning rate? Like we'll take on the log scales. Like we will first see on these value and just scan through all the data points, and we'll see how our model is working. So let's suppose our model is working fine at 0 0.1. Then we will try with some other nearby point of 0 0.1, that is like 0 0.05 or 0.15, and we will just check our loss function, like where the loss function is coming minimum. So we can choose, uh, first we will just choose the like nearby point using the log scale, because there are lots of point. If you are going from 0.001 to 1, like there are infinite number of points, and it will be very tough to choose the learning rate. So first we will just select value depending on log scales, and then we will find the nearby points there. Okay. And also, like when we are moving towards the convergence, then we can also reduce our learning rate, because let's suppose this is our curve and we are moving towards the convergence. Okay, we are moving. So here we are almost reaching towards the convergence. So if our learning rate is too high, then it will like overshoot the convergence point, and it will reach. Now again the loss function will increase. Now we will not get the minimum loss function. So what we will do at this point, let's suppose this is the point. Here we will just reduce our learning rate. Okay. So it is always good if you reduce the learning rate after some epochs, or like uh, or if you find that in the next step the learn, like if you are here, if some loss is there like L1, in the next step this is L2, this comes here, And if you find that in next step L2 is greater than L1, then in that case you can reduce the learning rate. Okay. If L2, like this is the point corresponds to, this is x1, x2. Let's suppose x1, L1, x2, L2. When you find like L2 is greater than L1, then you can just reduce your learning rate. Okay. So also you can do, you can just, there is one way, like you can half the learning rate after some epoch, let's suppose 5 epoch, and like you can do the exponential decays also. The first way is you can take the step decay. In this, you can reduce the learning rate after some epoch. Okay. In the second, like what we can do, we can like half the learning rate, or you can reduce also, depending on your choice. When error at next step is more than end of the previous. Okay. This is the step decay. Now, second method to choose learning rate, that is exponential decay. In this, what we will do, as we will move forward towards the convergence, we will decay our learning rate. So our learning rate will become, this is eta, that is equal to eta naught to the power minus k t. Okay. Here k are hyperparameters and t is the step number. So what we will do, like as t increases here, as t increases, our eta will decrease. Okay. As t increases, our eta will decrease. Why? Because eta is equal to, that learning rate depends decaying exponentially. So when t increase, it will become learning rate to the power minus kt. So if t is more and this power is in minus, so it will decay. So and like learning rate will decrease, and naught is the learning rate in initialization. So this is our initialization of learning rate. Now coming to the third, that is 1 by t decay. We can also decay the learning rate by 1 by t. In this, like we can take as reciprocal, that is 1 plus kt. Like and not eta naught is our initial learning rate, and as t increases, we will just decay the learning rate, and that is the reciprocal. Like that is 1 by 1 plus kt. So it depends on 1 by 1 plus kt. So here our learning rate is reciprocal of t. So in this way we can choose the learning rate. So I guess today we can stop our lecture here. If you have any doubt, then you can ask. And even these videos are recorded and it will be uploaded on YouTube. So in the YouTube chat box also, in YouTube also you can comment. Like if later on, if you see this live tutorial session on YouTube, if you have any doubt, then you can comment there on the YouTube. I will reply to the your doubts. And so we'll meet on the next weekend, that is on Saturday. Thank you everyone for joining. Bye bye. Okay, thank you. Bye. Bye bye.